Okay, so now we've kind of talked about the convolution. The next component is the max pooling. So this is the filter, and this is the, after we apply this filter to the image, right, we generate the corresponding feature map. And the next step is do the pooling, right? And the pooling operations is very simple and straightforward. So you basically specify the size, the pooling size, right? So here we'll do by a 2x2 pooling, right? So we divide this, the feature map into a 2x2 square or cell, and we just here we're doing the maximum pooling, right? So we take the maximum, okay? And this for this cell, then we do this for this one, and we continue, okay? So we only keep the largest value in the cell, and then we end up with a reduced size feature map, right? Or before we have a 4x4, now we end up with a 2x2 feature map, right? Reduce the size by half. Yeah, similarly for the other feature map, right? So we do the same. So if you have more filters, right? Let's say you have 100 filters, then you resulting 100 feature map. Then the pooling will be done, performed for each of these feature map to get a reduced sized feature map. Okay. So here basically means you have a, after the max pooling, right? You basically reduce the image, the feature map to a smaller size. Okay. Okay, so the pooling does not reduce the channel size. So you just, if you do, because you only do in the spatial domain, right? You reduce the space by half, but the number of channels still keep the same. Unless you do the channel-wise pooling, then you will reduce the number of channels. But here we're only considering the spatial, right? Reduce the spatial size, by half. And then the number of filters or channels will be kept the same. Okay. So what's the purpose of doing pooling, right? So we mentioned, right, this can reduce the spatial size, and then it can reduce the number of parameters, right? And because, as we observe, the object in the image, if you reduce the size, doesn't change, right? So by doing this kind of pooling, reduce the size, we are able to, promote computation efficiency and reduce the number of parameters we need to optimize. And also, this can increase the receptive field size gradually, right? Let's consider if you keep using a kernel size of 3x3, right? And if you after the first convolutional layer, right, you apply the max pooling, you reduce the size by half, and you are still using this 3x3 kernel on this reduced size image, right? Effectively, you are looking at a larger region, right? Because your input image reduced by half, right? But still, you're using the same filter size, then the effective receptive field size is going to be increased. So in this way, we are able to get more, towards like a global information, right? Not just always focus on this very small 3x3 local region, right? Because then you only limit to the information to this small region. But if we reduce the size and the receptive field size increased, then we are able to capture more global, information. So that's the purpose for doing the pooling. So there actually another way to reduce the feature map size, besides using the pooling. Another way is to consider, convolution with a stride that is greater than 1, right? Maybe you can using a larger stride like 2, 3, or even larger. This will also reduce the feature map size. Okay. And in the previous example, we take the maximum, right? For each of the cell, we take the maximum value. But in practice, you can consider other mechanism, right? Maybe, take the average right? This is kind of considered the average pooling, right? Rather just take the maximum, I take the average of those 4 values and, make a single value. So this is called average pooling. Okay, so yeah, the max pooling is most widely used, but definitely you can try, like average pooling as well. Okay, any questions? Okay, great. So after this, like convolutional layer, max pooling, reduce the size, eventually we also have a layer called this flatten the feature map, and then maybe append a couple of layers in the fully connected fashion. So here's basically what do we do, right? So maybe after the towards the end, right, the feature map size become very small, right? In this example here, we have like a 2 by 2 spatial size. Okay, then what we do is for each of the feature map, we flatten them all into a vector, right here, 4-dimensional vector. Then for another channel, we do the same, and we kind of concatenate or stack them into this large vector. And then we can consider this is like a giant vector and append it with maybe a couple of hidden layers in a fully connected fashion. Okay. So in this sense, we try to learn this kind of interact with each of the neuron, right? So make a more global information can be captured in this network. So that's pretty much kind of summarize, right? What is the main component? What's the process of the typical convolutional neural network? And just like the fully connected neural network, right? We also have this output layer, right? So we're using the softmax to get the very nice interpretation, right? Because we want to have some output we can interpret, not just some random value, right? So as we talk about, the probability is a nice way to do the interpretation. And so we want the value of this neuron output to be between 0 and 1, and all of them can do sum equal to 1, okay? So those are the basic components for the CNN. And we also have another component for doing the network optimization, right? Once we have specify all these structures, right, these layers, kernel size, etc., and what left to do is using the training data to train this network, right? So we use the loss function trying to define or kind to measure, right, how good the network is performing during the optimization. And this is the like a general term for the loss function. So here you have this, we're using F, we consider network as a mapping function, right? Mapping the input to the output, right? So we use F to indicating the network, and we use this W to indicating the network parameters, right? So those weights and bias terms for each of the neurons. So we're using a capital W to indicating the set of network parameters. And Xi is the input, right? So this will give us a prediction, right? We have the input and the network weights, and this will give us output of the network. And as we mentioned, if we're doing the supervised training, right, we have a ground truth, right? So this is if we're doing image classification, this will be the corresponding classification label for one particular example, right? So then we can compare the prediction and the ground truth, right? Of course, we have to define a loss, right, or metric, right? How we can measure, how we can compare, calculate the difference between the prediction and the ground truth. And we do this for all the samples in the training data set, right? So we have n samples, then we compute across all these n samples and using them as the total loss. So the goal is to minimize the loss so that at the end, hopefully we are able to and the network can reach a local, or hopefully we can reach a global, ideal case, a global minima, right? And we can using this network for inference or testing. Okay. So yeah, here is a figure showing that we are doing this digit classification, right? So we have this target and we have this prediction, and here we're using the simple mean square error. So as the loss function to optimize that. And we also have another very popular loss called a cross entropy loss. And if from classical machine learning, right, the logistic regression, this binary cross entropy is used in this logistic regression, or sometimes you will see referred to as the log loss, right? So this can be used in the general multi-class classification. So the general form is the sum of yi log yi hat. Okay, so this yi hat is the prediction. Okay, yi is the ground truth. Okay, and if you look at the log function, right, it can be the base of 2, or we can use the natural log. But they pretty much the same. Here, because of the output, right, we interpret as a probability. So we know that this y hat is going to be a number or value between 0 and 1, right? So on this graph, then we only have to care about this region. Okay, I highlight here with this square. And we know that the ground truth is a one-hot vector, right? So, let's take digit classification recognition as an example, right? If the input digit is 9, so we structure it as like the 0 is going to be the first position, 1 is going to be the second position. Then if the input is 9, right? So the one hot is going to be 0, 0, only the last value going to be 1, right? Indicating a digit of 9, right? So let's look at, I'll give you an example here. If this yi hat, let's say it make a perfect prediction, just the same as the ground truth, right? This yi hat prediction. So we can go into this, put this value into this equation and compute the loss, right? So the first 9 position is going to be 0 because the y is going to be 0. So we don't care what kind of value that is. So the last one, we have 1 multiplied with log yi hat, which is also 1, as I mentioned, right? Let's just consider that's a perfect prediction. So log 1 equals to 0, right? So here, the entire summation here equals to 0, right? Which means incur a 0 loss, which is what we want, right? Because the network will make an accurate prediction, right? We don't want to penalize that, right? Only if you make a mistake and I want to incur a loss to penalize, right? Maybe you need to try something different to improve the result, right? Okay, let's still using the digit 9 as an example, right? In this case, the network didn't make a perfect prediction, actually make a very bad prediction. The prediction is make a digit 0. So 0 has a probability of 1. The other has 0, right? And what happens, right? So here we have this yi here, the last digit position is going to be 1, right? This is ground truth. And here we have this log 0, right? Because we predict a different digit, right? The value corresponding to the class of 9 is 0, right? If you go here, right, look at the 0 point here, the corresponding value, the log value is approaching infinity, right? The negative infinity. But here we have a minus sign here, right? So we sum them together. Actually, there's going to be a positive infinity loss, right? Because you made a totally bad decision or prediction, right? And you are very certain this is like 100%, this is a zero class or maybe other class. So this is very bad. And if you make like, okay, 0.5, right, then you still gonna be penalized, but not a lot, right? As compared to if you make a decision of zero. So this way we can adjust the right how much we need to penalize the mistake this network is made. So this is how this cross entropy works. Okay, so I hope you get a sense of these the rationale behind this cross entropy loss. Okay, so here just basically substitute this squared loss with these cross entropy loss, and we can again train this network and for digital recognition. Hopefully, the model is able to have a very good prediction, right, as compared to the ground truth.